right, the first question we're going to do is actually an electrochem question. Let me go ahead and find the key that I have printed out for this one. This is 2006. All right. So, first question. Answer the following questions about a voltaic cell. Well, let's talk about what we know about voltaic. Okay, voltaic, spontaneous or non-spontaneous? Okay, this is spontaneous. Now, another word that you could have used for voltaic is galvanic, and they'll use them interchangeably. So just make sure you kind of catch that. So, voltaic is spontaneous. Now, there's also this factor, E naught. When it's spontaneous, it's what is the unit for this? Voltage. Do you want to produce voltage? You want electricity? Yeah. So you want it to be positive. So that's how you want to think about it. So right now, simply by that one word, we've kind of figured out where we need to go with this. It may not help us at all. It may help us a lot, but we have a direction. All right. A voltaic cell is set up using aluminum to aluminum ion as one half cell and tin to the tin 2 ion as the other half cell. The half cells contain equal volumes of solution and are at standard condition. This is very important. Standard condition, what's your pressure? 1 atm. And what is your concentration? 1 molar. Very good. So 1 molar. Then it says write the balanced net ionic equation for the spontaneous reaction. This is the difficult part. This is when you need to use something to tell me which one's going to which, because in electrochemical cells, one's being oxidized and one's being reduced. Well, the way they have both of them written, what are both of them doing? They're going from neutral to positive. So is that oxidation or reduction? They're both oxidizing. Well, you got to figure out which one is being reduced, right? So what are you going to use? The reduction potentials, okay? So since you're using the reduction potentials, that's something that you're going to have to look up. They give you the reduction potential chart on the AP exam. Let me get this out so I can look at it. All right. Now, so here's the crazy part. They give you, this is reduction potentials. So these are being, we said these are being what? Oxidized. So we need to figure out, now, one of them is going to be reduced. Which one will be reduced according to the reduction potentials on the chart? Very good. The reduced one on the chart, the reduced one on the chart is the most positive. Is the most positive. So Al3 plus going to aluminum on the chart is, Wayne, do you see it? Negative 1.66. And now why am I writing these backwards from what the equation has? That's oxidation. We want the reduction values, right? Going to Sn is equal to what? Now be careful because there's two different ones. There's Sn4 plus to Sn2 plus. Yeah, we want 2 plus to neutral. There, okay, sorry. Negative 0.14. Now notice what I said. Not positive, but most positive. But they're both what? They're both negative. But which one is, quote, more positive? Okay, so this one right here is going to go through what? Okay, this one is going to go through reduction. And this one's going to go through what? Oxidation. So if it's oxidation, what do you do with the equation and the sign? You got to flip it all. Okay, you got to flip all this. So I'm going to set this up as an actual reaction. Okay, so give me just a second, and if you want to write this into the bottom, but I'm actually going to set it up how we've always set everything up. So let's go ahead and write. Let me get this shade off. All right. We've always set up our red capped OA and our ox and Ra. Now, which one did we say was going through reduction? 10. So Sn is going from what to what? 2 plus going to Sn neutral. Now, Miss Snell taught me this one because I heard her say it and I was like, I love that. you always balance for atoms and charge. And she taught me this. Electrons in the reduction go where the reactants are. Does that make sense? Reduction, the electrons go where the reactants are. So does that help? Or if you, the common sense approach, you have two positives. How do you make it balance to neutral? You need two negatives. So we've got the reduction half reaction written. Now we need the oxidation half. So oxidation means it loses an electron, so it must go up in charge. So this time, what's it going to look like? Very good. It's going to go from Al to Al 3+, right? Oops. Al Al 3+. Now, I just said that the electrons in reduction go to reactant side. Well, the electrons in an oxidation go on the other or opposite side. If it works, it works. Okay. And again, and another way to look at it, if this was neutral, the only way to balance it is to put 3 electrons over here. Okay. So far, do our atoms balance? We have one SN, one SN. We have one Al, one Al. Do our electron, or do our charge for each one balance? So we have 2 electrons plus 2 protons, neutral and neutral, neutral and neutral. The second part, and this is the last is the most important, do our electrons balance? No. This should be that rule that I always told you about balancing equations, the 2, 3, 6 rule, right? So if you got a 2, what do you put? A 3. And if you got a 3, you put a 2. So atoms, charge, and electrons all balance now. What do you do after this point? Add your half reactions. Add your half reactions. But here's the most important part, and I really don't want you to mess this up. Make sure you distribute, please. Please make sure you distribute. So you have 6 electrons plus 3 SN2 pluses plus, now going to the bottom, 2 aluminums, and it goes to 3 SN metals plus 2 aluminum 3 pluses plus 6 electrons. Now what can you cancel out of that? Electrons. That is, right here, your balanced equation. Yes, sir? Personally, on what they have, here, let me show y'all what they, let's see. Start this. The only problem is it's going to take forever, so I may have to pause the video. So give me just 1 second. So you can see question 1 right here. It says 3 SN2 plus 2 Al yields 3 SN. So really, all they asked for was this. You can scratch work it and show them this. So 1 point earned for the correct direction, and 1 point is earned for balanced net equation. So that's 2 points simply by doing this. Okay. Now, did it take a lot of work to get here? Yes. What you really need to just show everything. Okay. So you really need to show. So if they ever ask for a balanced net ionic equation in a redox reaction or an electrochemical cell, you must do the process that we just did. Okay, so that's this part. Now, if we go back and we look at question A double I, determine the value in volts of the standard potential of the spontaneous. So not only if we didn't really have to say this earlier because they tell you it's spontaneous, but since we've already determined it was spontaneous, what does that tell us about this? It's got to be positive number, right? Now, right here, we've already worked out. So what I would really do, and I taught y'all this in the beginning, is why does that keep popping up? Well, yeah. There it goes. Okay, I have to hit the check mark. Okay. When I'm doing this, what I would personally do is I would go ahead and write these values down out to the side because they're probably going to ask you for them. If you're doing electrochemical, they're probably going to ask you for them. Now, this turned out to be negative, what was it, 0.14, right? Now, in all oxidation reactions, from the chart, flip the equation and what else? And the sign. Now, this is huge. Do you multiply these values by the 3 and the 2? No, 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 no. No multiplying. No multiplying. Now, what was the aluminum value? Negative something? All right. Now, but what do we have to do to it? Positive. Flip it. So it's positive 1.66. So this right here is the E of reduction. This is the E of oxidation. I guess to make it a little bit easier if I just come back over here. All right, so let's do this. So we have positive 0. Change this. We have positive 1.66 minus 0.14. Is that what it was? Is that right? Yeah. Okay. And then just add them together. And you should come up with a positive 1.52 volts. You have to put the positive. Now, no, you don't necessarily have to, but I would just to make sure. Okay? But you do have to include the volts. Now, while we're in this, what does a volt equal? Very almost joule per coulomb. Close. Very good, though, Joe. Joule per coulomb. I would definitely know that just in case you ever need somehow to convert joules and volts and coulombs. I would know that one. Say that again? Do you? Yeah, because you're going to need joules. That's right. Very good point, Wayne. What Lane just said is you're going to need, in part 3, that delta G is in joules, so you're going to need that for delta G. Very good point. All right, so talking about number 3, calculate the value of the standard free energy change, which is delta G. Now, include units. Guys, if this right here, if you don't do the units, you miss the whole point. Let me see what it says. It says 1 point is earned for the correct mole ratio, and then it says 1 point is earned for the correct answer with the units, with correct units. So it's 2-point question. But you get 1 point for the moles and 1 point for the answer with the correct unit. So it says with correct units, so that is going to count. This one, it says 1 point is earned for correct answer, and it says potential must be positive. So as long as it's positive, you'll get the answer right on this one. All right, so let's look at 3. Now, what are the 3 factors that tell you true spontaneity? The geek factor, right? So we should know this. We know that E is positive, gangsters are negative, and K is greater than 1. We can relate all 3 of these equations. Y'all seen me write them before. Why does that keep popping up? Okay. So, again. So, delta G is related to E by what? What? In phase. Very good. Negative. I missed the F. Negative or Nephi, if you prefer. In phase. How is delta G related to K? Rat link. Nope, I missed the LN. I keep missing stuff. LN, okay. Now be very intelligent here. How is E and K related? Now, is it positive or negative, Ratlink? Positive. Very good. Why? Because what do the negatives do? Cancel. So you have N Phi equals Ratlink. Now, I've honestly never seen an equation like that. How I've seen it, I have seen that. Okay, but where did that come from? Just rearranging it algebraically. I have seen this, and I think, as a matter of fact, it might potentially be on the equation sheet. That's oh, what they have this version. Let me show you what they did. They have. Let me move to the next slide. Let me show you. Really? They actually have 0.0592, which is, that's the exact same equation. What they have done here is they have interchanged R and T at standard conditions. Okay, does that make sense? Okay, so this is the equation we need. Why do we need this equation? Because you have E and you want delta G. Now, N is the what? It's the number of moles, but what it really is, it's the canceled number of electrons. Because that's really the moles of electrons. So it's the one that you canceled off. In this equation, what was it? 6. Okay, so it's 6. Now, what was F? Faraday. Which was what? 96,500 coulombs per mole of electrons. So coulombs per moles of electrons. And guys, if you don't remember the units, it's on your equation sheet. That's where I just got that. It's 96,500 coulombs per moles of electron. And then E, of course, is the electric potential, which is in what? Volts. And what is a volt? A joule per coulomb. So let's plug in what we know. So we know delta G is equal to negative N, and we said it was what value? It was 6 moles of electrons times 96,500 coulombs per moles of electrons. And it was, what was the electric potential again? Positive 1.52. Now, here's the deal. You can put volts in right there, but the problem is if you put volts in, where's it going to cancel? It won't, because what's moles of electrons going to do? They're going to cancel. But if you put in joules per coulomb, those coulombs are going to cancel, leaving you what value? Joules. And what does delta G always give it in? Joules or kilojoules. So that's what you're going to have to do there. Again, that's why we need to know what volts equals. Is that with me? Okay. So when you do the math on this, you should have gotten negative 8.80 times 10 to the 5th joules. And this is where AP is making me mad. It's what? Per mole of reaction. Very good. Per mole of reaction. And again, and for some reason, they want that. And I don't know why. And I know it's one reaction, and it's 1 mole of reaction. So every time you make this reaction happen, how many joules of energy are you going to get? That. So if you do this twice, you're going to double it. If you do it 3 times, you're going to get triple that. So I get the point of it, but I still think it's useless in the equation. Now, that's not, it's probably the easiest way to write it. Or if you want to write it in kilojoules, I'm going to write it up here. It was negative 880 kilojoules per mole of reaction. Again, I would just leave it to the 5th, personally. Here's the biggest thing. Since you knew that E was positive, how did you know that delta G had to be negative? Because E was what? This was spontaneous. We've already said when E is positive, it's spontaneous, and what is G? Negative. So keep those factors in mind. You move it 3 places. So if you move 1, 2, that would to the 3rd, which is kilojoules. So if you move this 1, 2, that gives you 880, and it would be to the 3rd, which is 1,000, which is kilojoules. You with me? Okay. All right. Let me bring that back just in case I need it. So far, you've earned, you would have earned a point for the 6 moles of electrons. Here, let me just show you this. You would have, wow. Now I was just going to do this. Try to not break my pencil. You would have earned a point for this right here. That's 1 point. And then this with the correct unit would have been the second point. So 1, 2, 3, 4, 5 points so far out of a possible 6, 7, 8, 9 out of 9. So 5 out of 9. If you get 5 out of 9, you're doing fairly well with this. 5 out of 9, you're doing fairly well. Okay, let's go back. So 3i. Calculate the, no, excuse me, 4. If the cell operates until the aluminum ion concentration is at 0.108 in this cell. Now, we've already determined what did aluminum go through, oxidation or reduction? In the oxidation. Now, just as a curiosity and just to review, what I want to do, and I should have already done this, and I'm sorry I haven't done it, but I really want to review this with you, and that's drawing voltaic cells. I want to practice in that because they may ask you to draw it. So, remember, what voltaic cells are always in 2 different containers separated by what? Salt bridge. Very good. What always goes in that salt bridge? KNO3. And you have, what are these things called? Yeah, they're electrodes. Okay, they're electrodes. And it's connected by a metal wire with a voltmeter on it. And it's attached. Now, we always set up ours alphabetically. So this was ox and Ra, red, cat, Oa. How do electrons flow? A to C, anode to cathode. So our electrons are going to flow like this. So electrons, how do they flow in the internal circuit? They flow backwards. Okay? That's how electrons flow. So it's a continuous cycle, right? What? If they ask you about the internal circuit, they go from cathode to anode. They're just backwards because it's just making a big cycle, right? Now, what is the purpose of the salt bridge? Neutralize, right? You want to maintain charge. If you don't have this, it doesn't work. You want to balance the charge. All right, so what happened right here? What was our oxidation reaction? Was it aluminum? So it was Al going to Al3 plus 3 electrons. This is the anode. It's anorexic, so what's happening to it? It's getting smaller. So that aluminum piece of metal is falling off. What's falling off into this solution? Aluminum ions. So think about it for a second. Of this salt, which one of these is coming over here to maintain balance? Why is it the nitrate? Because it's negative. So that NO3 negative is coming over here to hang out, to balance that charge. Okay? So that's aluminum. What is going to be over here? The tin. Now this is the fat cap. So what's happening to it? It's getting bigger. That SN2 ion is sticking. So what's going to come into this one? The K plus, right? To balance that charge. Because positives are leaving and it's full of... Here's the part I really want you to grasp. Every time an aluminum drops off, how many positives does it drop? It drops 3. How many nitrates would you need to balance that out? 3. Very good. They may ask you something like that. You need 3. How many positives would you need to balance that 10? 2. Just because you've got 2 leaving, you've got to rebalance it with 2. Exactly. Okay. All right. So over here we know it was SN 2 plus going to SN neutral, and it was 2 electrons. So that's. Let me think. Is there anything else we talked about with this? I don't think so. And again, that's how you would draw this. When this reaches 0 volts, very good, Joey, you are at equilibrium. It doesn't die, you've just reached equilibrium. Okay? If they talk about anything when voltage reaches 0, don't say it's dead. Don't say anything about it. Say you have reached equilibrium. So that's a good point to make. Again, all of this is review. Hopefully that should be clicking with you. Sir? Yeah, that's exactly what this is. Yeah, what happens when you plug it in is this is voltaic galvanic. It reverts back to electrolysis, and it literally goes in reverse. So what happens is this falls off, this jumps back, and it's a lithium-ion battery, so it has to do with lithium and things like that. It's not to this crazy degree, but it is somewhat to this. It's just a reverse. So you have all your charges build back up, and then it depolarizes again. Okay. Now, what makes it burn? That's all in your computer chip. Okay, so again, I just wanted to review that with you just to make sure that we were good with knowing how to. This is drawing an electrochemical cell. Is what this is called. Okay, part 4. If the cell operates until the Al3 concentration is 1.08 molar in that half cell, what is the concentration in the SN2 half cell? This should be pretty simple. Stoichiometry is all this is. All this is a mole to mole ratio. That's all this is. We wrote the equation. What was the balanced equation? No, I have it right here. So 3SN2 plus 2Al goes to 3SN. Seth, I think you missed this part. This was in part 1. Plus 2Al 3 plus. So they're asking you if the concentration goes up. Now, how do we know it went up? Because right here, they told you is at what conditions? Standard. And what concentration is that? That's 1 molar. So it must have went up, right? So we want to know what now, so what did that mean the SN had to do? Had to go down. So let's figure it out. So we're starting with 0.108. Now, what does molar equal? Huh? Moles per liter. Now, we always said, how do you compare moles to moles? You can also compare molar to molar, right? Because as long as the volume doesn't change, then you can still compare molar to molar. So I'm just going to write moles over liters just to kind of make an effect here. And again, moles is on top. Where does it have to go? You got to go on bottom. Sorry, I wrote the parentheses. I've been doing it in honors all day. Okay, and this is AL, and this is SN. Now, so what's going to go on bottom? 2, what's going to go on top? 3, very good. Now be very careful. Significant figures. How many do you have? 3, very good. Do what? Hang on. Let me think about this for just a second, because they have something a little bit different. No, when I'm thinking they've got something different here. So hold on, let me pause the video and fix this before I mess this up. Yeah, absolutely. This is let's restart this process over. They tell you that it was 1.08. What we know originally it was 1 molar. So what they're really asking you for is how much did it change? Okay, how much did it change? Well, it originally was at 1.00. Well, it went up to 1.08. So it changed as a difference of 0.08 moles per liter. That's how much it changed. So what we're going to do is we're going to find how much it changed and then subtract it again from the original concentration. So this change, what did this change in aluminum? How did it affect that? How did it affect that? That's what we're really looking for. So when you do this, you get 0.12 moles per liter of SN2. 2 plus. Well, again, what did it originally start at? It originally started at 1. So since it started at 1.00, that means it changed this much. But again, we said if this up, then what did the other one have to do? It had to go down. So you'll subtract, which gave us 0.88 molar. Okay. Again, it's a weird way to think about it, and I personally, I would have started this the exact same way and came up with something totally different. I would have. But again, they're asking for a difference. And since this changed 0.08, that's what they're looking for. They're looking for a change. How much did it change? Okay. All right, this last part. In another voltaic cell with the exact same setup, this time they've changed the concentration of one of the ions. They've changed it of the 10 ion. Are we at standard condition anymore? What was that crazy thing I kept saying? We are at quasi conditions. What's wrong with that? We're quasi, right? We're no longer at standard conditions. There is a formula on your formula sheet that's on here, and I've already let's see. Since it says standard conditions and it says it's at 25 degrees, literally on your equation sheet, it says this: E naught cell is equal to negative 0.06. Now, on the equation sheet, it says 0.0592. Don't do that. Just go 0.06. Okay, it's a lot easier to use. And it says N and the log of Q. A log of Q. Now, we know that K and Q are the same thing, right? What do they always equal? Products over what? Reactants. And then here's the key part. Don't miss this part. What else do you do? Raise it to the what? Coefficients. Now I'm going to rewrite the reaction one more time. It was 3SN2 plus 3Al goes to 3SN plus 2Al 3 plus. We've said this a million times. What never gets written in K expressions? Solids. There are two solids in this equation. What are they? Very good. Those two, right? That's not a 3. That should be a 2. I'm sorry. I messed that up. That needs to be a 2. All right. This still doesn't matter. You're still canceling it out. So, we need to use this equation and plug in. So, if I were to write Q based on this reaction, what would it look like? Almost right here. What would it equal? Raised to what power? Second. And then 10 ion raised to what power? 3. So this is going to get plugged in. Do we have numerical values we can plug in for this? All right, so I'm going to change screens, and we're going to solve for this. Come on. All right. So writing it again. E naught equals negative 0.06. No, excuse me, not just Q. All right, we've already solved for Q, and we said it was Al 3 plus squared over Sn 2 plus cubed. That is Q. Now, what is N again? The number of moles balanced, right? Cancel. What was it? 6. And then we're going to take the log, and they gave us the concentration values. Aluminum was 1.0 squared, and then it said the 10 ion concentration was what? in the question. 0.01, and that is cubed. This is a difficult calculator problem. It just takes some time. It takes figuring it out. But if you did it, see? Okay, hold on. Please don't tell me I messed this up. Guys, I did. I forgot E naught, didn't I? All right, here. It's an easy fix. It's E cell equals E naught cell minus. This was the original. That's what you found originally, right? What was that value again? Guys, I'm sorry. I jumped ahead of myself. This right here is the equation that's on the equation sheet. And again, if you would have seen that, I overlooked it for some reason. Again, this was the original one you found. Go back up and part double I, this is where you would have found that. So when you do this math, the math they got, I'm just going to show you how they broke it down on the key. 1.52 volts minus all of this right here equaled 0.0592 volts. And so the answer was 1.46 volts. This is E cell. Again, I'm sorry about this part. I messed that up. I wasn't paying close enough attention. But the major part I want you to get is hopefully you would have known to use this.
LaMarcus Bishop,
because
if you're
why?
in the building, please come to the front office. LaMarcus Bishop, if you're in the building, please come to the front office.
We use this because what? The concentrations were not at 1 molar. That's why we did that. They changed the concentrations on us. So as soon as they did this, we had to use Q. Wayne, do you still want to see the key? Okay. All right. So I'm going to show you all the key of. Okay. This is what they did for part. So you see what I'm talking about? How they said the change in concentration of the SN2. So they got the 0.08. And again, this moles per liter is the same thing as saying molarity. And then they did the mole to mole ratio. They got that, and then they subtracted it from the original concentration, which gave you 0.88. So again, that's 1 point for that. And then this bottom part, this was the exact equation we just saw. And I said, remember, instead of saying 0.0592, do 0.06, which is the exact same thing you would have gotten here. For some crazy reason, all of this worked out to be the exact same. I have no idea why that happened or how it happened, but it did. So answers must be consistent with part 1. So here's the cool part. What if you would have messed the voltage up? The 1.52, what if you would have got that wrong? As long as you would have got the rest of this, BOA would have earned you all these points. So 1 point is earned for the proper exponents, so solving for Q. You've done that a million times. You should have been able to got Q. It was 1 and squared and 0.01 cubed. 1 point earned for the correct substitutions of concentrations. You got 2 points for doing Q. Yeah, we would have got this right because AI. With AI, I think it's talking about the exponents because AI was the balanced equation. You know what I mean? AI was the balanced equation, and it should have been consistent with part I and double I, because this could have been different. So if you would have messed the exponents up and the voltage, you still would have earned a point. But let's say you got to this point and all of a sudden you miraculously come up with this. Okay. So again, you would have gotten the point for it, and then finally 1 point is earned for the correct answer. I personally think if you could have figured out to use Q, you could have figured this whole problem out. I really think minus IV, I really think y'all could have earned 8 of 9 points based on what we've done. Yes. Well, you would have had to have done the equation. Let's say you screwed up the math. That's where you would have lost the last point. You see what I'm saying? Okay. All right. And again, it says calculated value in volts. Just because it says in volts, still put it. Make sure you always put the units. That's huge. Don't lack on the units. All right. I know we're running short on time. I do want to cover the kinetics one though. I do want to cover that one. Yeah. All right, here's the deal. Apparently, in the review session, Mr. Hand taught y'all how to do the algebra way. Very simple. I wasn't there for that, and so I personally don't know how he made it look so simple. And the reason you can't do table logic with this one, you can find the order of this one. All right, so when I hold these constant, this one does what? So 0.52. That triples right here, and that one also triples. So when they both triple, what order is that? That's first order. So I get this one. I don't know how he did table logic. Or not table logic, but the ugly algebra. Taylor, do you remember how to do it? For Mr. Hand? Okay. Nolan, do you remember how? I really wish... Let me see... That's what I'm thinking. I'm going to try. See, that's the problem. This turns out to be 3.6. It's a little off. Yeah, when they're equal. Yeah, they are both first order, but there was the algebra method. Let me just show you how it's done, based on what they have. All right, so this is what they did. They did rate 3 equals the K of I3. No, let me over rate 1 over the exact same thing. K of I minus of the first experiment and CLO minus of the first experiment. And then they just plug the numbers in. So it would have been the rate of 3 is 0.596 divided, here, let me just stick with the same colors. .596 is equal to K, and it is 0.016 raised to the x. This is 0.061 raised to the y. That's 596. All divided by 0.156 equals to k 0.017 x. Again, I'm getting every bit of this off the table. 0. All right. What they then did is they then pulled this down. They did that math, which was 3.82. Now, here's the part what we're looking for. We're looking for the order of this one, correct? Because we've already determined that this was first order. So it's written second. Do you agree with that? So what we're going to do is we're going to keep these intact, and we're going to go ahead and do the division. What can the k's do first of all? You can cancel those. But we're going to pull this down and do that math. And the x's will do what? Cancel. So it's 0.94, and it's still, but now that I'm seeing it, it's kind of making sense, but I still don't know the best way to approach how to do this every single time. So again, we just pulled that one right there down. And the reason why we pulled that one down is because we are searching for this order, which goes in right here. That's the one we're searching for. Okay. So then they did the algebra. They divided that off and got 4.06 equals. And then they did this math and came up with 4.1 to the y. Now, what would y have to be to make that happen? Y would have to be 1, right? So if 4.1 was raised to 1, now I know it's not going to be exactly 4.06, but it's close enough, right? So what order is it? First order. And I know that's crazy, and I know it's weird. And again, I wish I could have been there to seen him teach this, but that's what it is. I don't know, it's ugly algebra. That's what I kept calling it. So you have determined what it is. Now, part I, regardless of what you come up with. So you got it all? This was when you divided that into that. 3.82 divided by 0.94 is point. You with me? That's where that 0.46 came from. And then this 4.1 came from dividing that. Is 4.1. Yeah, I get it. Yeah. But we have figured out both of these are first order. And I really hope you can write a rate law. You would be shocked at how many people messed up the rate law. And let me show you why they kept messing it up. They kept writing this. Do not write this. This is what they wrote. Wayne, I heard you say it. What's wrong? There's no K. Everybody forgot that baby K. Everyone, all those great questions that I saw in the mock exam that I was grading, everybody was missing that. And this is kinetics, and I always like putting the order of 1. You don't have to, but again, it's a good thing to do. Calculate the value of the rate constant and specify the units. Sir. What do you mean? What if baby K was 1? I have no idea. Oh, no. That is true. If baby K was 1, then rate would equal all of that. But it would be, I don't think that would ever happen though. Now, calculate K. We want to calculate this. What can you do? Yeah, you can rearrange. So K is equal to, right, over I minus to the first, CLO minus first. Where do you get your information from? Pick a row. Pick a row. I always said pick row 1. That's just what I always said. So if you'll put that in there, if you'll put this in here, and you'll put this right there, here's the most important part. What is our overall order? Overall is 2. And this was the finger rule. You hold 2 fingers up, put one that down, that tells you how many watts on the bottom. So remember the units for K was equal to a number over molarity times times. Now, what is your time unit in this particular thing? Sitting right there. So it's seconds. So it's a number over. Now, why is there molarity in this one? Because this is a overall second order. Hypothetically, let's talk about it. What if it was an overall first order? Just so you can see it. It would be K equals 1 finger up, 1 finger down. How many molarities? None. It would just be a number over time. That's for first order. If it was overall third order, it'd be molarity squared. Okay, hopefully that's triggering back off. So when you plug those numbers in, let me just tell you what the answer is so you can go home and get it. Why am I looking? Am I looking at the wrong question? Oh, I went up. Okay, there we go. I was going down. I needed to go over. So when you plug those numbers in, you would have gotten 610 molarities per second. And again, the reason it's molarity over second is because it was overall second, and there's a molarity on the bottom. 2 fingers up, 1 finger down. That tells you that. So that would be K. That would be K. This next one is really easy, and I want to do it because it won't take but just a second, because they make your life fairly easy. It's right here. Dang. But this is very simple. Remember, kinetics, there was 2 types. There was differential and integrated. As soon as you see this, what type was it? Right? Integrated. And Wayne, this is what me and you were talking about earlier. If it was 0 order, what was it? It was just a concentration on the graph, right? Because we're looking for when integrated, we're looking for the slope of a what? Of a straight line. Yep, we're looking for a slope of a straight line. And whenever we plug these numbers in, we're trying to find the slope of a straight line. If it's 0 order, just the concentrations will do it. If it was first order, what was it? The natural log of the concentration. And if it was second order, it was the inverse or the reciprocal. Very good. The reciprocal of the concentration. Look what they gave you in the instructions. The kinetics of the decomposition reaction for study and analysis results show this is a ding, ding, ding. They have just made your life so much simpler. There's no calculations involved in this. So when we scroll down, it says, during the analysis of the data graph was produced, look at part 1. Label the vertical axis. That's easy, guys. All it is the ln of the concentration. Yeah, absolutely. That's what I would do. That's exactly how I would write it. As a matter of fact, what they actually have is the it's H2O2. I would put the reactant in there. Does that make sense? I would be so frustrated and mad is that they took points away from y'all because you didn't write that in there. You know what you're doing, but just because you didn't put it in there, I would hope they wouldn't do that to you. All right? And then what does it say are the units of K? We've already talked about this. What is your overall order if it's Ln? If it's first order, one finger up, one finger down. So it was what? Number over time. And in this thing, there's your time unit. So what was it? It was 1 over minutes. Now, what's another way to write that? Very good. Minutes to the negative first. Yeah. I mean, really, if you know kinetics, I think if I would have given this question on the test, I think y'all would have all slammed this. Because we did very well. Okay, here's, matter of fact, this question. Was this one of the questions I gave y'all? Was it? This was the, I think. I don't think it was a specific question, but it was close to triple I because I remember this question. On the graph, draw the line that represents the plot of the uncatalyzed. What does a catalyst do? It lowers activation and does what? Speeds it up. Well, when we're talking about time, when it uncatalyzes, what does that mean? It slows down. So what does that mean as far as time? It takes longer. That's it. That's it. That's it. Good luck. It would have to be. Yeah, it would have to be. That. You good? Does that make sense? Okay. So, again, I think, I could be wrong. This may have been the exact question that I gave you all on the test. I think I may have changed the numbers up a little bit or something. But anyways, y'all should have definitely hammered that question. But again, the key word there is uncatalyzed, speeds up reaction. When it's that means it takes longer. So it's just a down slope making it. And what I would honestly do is I would label it, because this is how they have it. Uncatalyzed. Yeah. You never know with these people. Don't let them take it away just because they're being snobby. All right, so hopefully that has helped for today.